Hello, everyone. Welcome to another wonderful day of chemistry. So today we're going to be using the structure of acids and bases to tell us about how acidic or basic a structure is, because there has to be a better way than seeing if it tastes sour or bitter. So when doing this, there's going to be a very common theme. In order for a strong acid to be good at losing a proton, it has to be unhappy where it is, and it has to be very happy as a conjugate base. So when we're looking at the structure of an acid, it's going to be important not only that we look at the acid itself, but at the conjugate base it forms. And a great example of this is looking at our halide acids. So hydrofluoric, hydrochloric, and hydrobromic acid. All of these look fairly similar. Only big difference here is going to be the size of fluorine, chlorine, and bromine. So when we're doing this, it's very hard to try and evaluate which of these acids may be weaker or stronger. There is some knowledge of, the length of this bond could give us some insight. And one of the reasons why is because what the length of the bond of the halide hydrogen bond really tells me about is the stability of the conjugate base. So if I have something like fluorine, it has a full negative charge, but it only has 9 protons to help keep that negative charge in place. So it turns out it's not exactly the most stable species. However, when I go to chlorine, now I've got 17 protons. So almost twice as many protons to help stabilize that negative charge. By the time we get to bromine, we've almost doubled the charge again with 37 protons. So as we increase the number of protons, it's easier to keep that negative charge in place as there's more positive charge to help counterbalance that negative. And it turns out if we look at the pKa's, we'll see a varied trend. So hydrofluoric acid is quite notable as it is the only one of our halide acids that's actually a weak acid. With a pKa of about 3.2, it turns out it actually doesn't completely break apart in water. In fact, you're going to have more of the hydrofluoric than you will of fluoride, which can play a key role in a lot of chemical processes. However, when we go to hydrochloric, this is our quintessential strong acid. It's much easier for that chloride to go out and be strong and be on its own because it's got that more positive charge to stabilize that chloride anion. And as a result, it's got a pKa of about -3. However, it looks like a pansy when you compare it to bromine. Bromine is quite stable on its own. It's large and in charge, big and stable. pKa is almost -9. So almost 6 pKa units more stable than chlorine. So one of the big things you'll tend to note is that as we go down in a periodic table, a lot of these elements tend to become more acidic. And one of the ways to look at it is what we're doing is as the elements get larger, you tend to stabilize that negative charge. So you can make a species just a little bit more acidic by making that charge a little bit more stable. And this comes into our good old periodic trends. Size helps stabilize. So one of the other common tricks we can do is take an acid and place an electronegative group on the acid. So this is going to pull more of the electrons onto the existing atom. So let's go ahead and we take something like water, the quintessential weakest of acids, pKa of 14. However, if I go to hydroiodic acid, now I've replaced one of my hydrogens with an iodine. And by doing so, I've reduced the pKa from 14 to 10.5. And one of the reasons why is instead of having a negative charge just on an oxygen like I do with water, now I've got a negative charge on that oxygen, but that iodine is going to be fairly electronegative. So it can help pull some of that negative charge over to the iodine. And this is going to help stabilize the species. A little bit of negative charge is easier to bear with some help from your friends. However, if we go to bromine, so bromine is actually more electronegative than iodine. So it can go ahead and bear a greater load, help stabilize that oxygen when it's left alone. So we drop that pKa unit by about another unit of 2. So a lot more acidic. However, if we go to our good old friend bleach, hydrochloric acid, now we've lowered that pKa unit by about another that pKa by about another unit as we've further stabilized that oxygen, because chlorine is more electronegative than bromine, is more electronegative than iodine. And it turns out this doesn't work with just stabilizing oxygen. You can stabilize any number of molecules, make it a little easier to bear a negative charge by having somebody who can help share the load. More electronegative, more stable. Now, do note that this is opposite from just trying to place that negative charge on these ions alone, where size will matter more. So it matters a lot whether you have to do it on your own or whether you get a little help from your friends. So if you want to increase the the acidity of any molecule, increase the electronegativity of the molecule. This will help stabilize that buildup of charge on the conjugate base. Again, it's less about the acid, it's more about the base. So we can also end up using some more complex ideas of electronic structure to try and predict a more stable base. So let's go ahead and take a look at something like ethanol. So ethanol has a very high pKa. It is very poorly acidic. It will not break apart in water. It will pretty much stay together as ethanol, because it turns out that oxygen doesn't like being negative, because it turns out those carbons are no help at all bearing charge, and in fact want to give oxygen some more. However, what happens if I end up placing another oxygen on the nearby carbon atom? Now, when I lose a proton, lo and behold, we now have that negative charge on that oxygen. But we have a resonance structure here, because I can move that negative charge over onto the carbon and pop it back up onto the other oxygen. And this is the reason why oxyacids are so powerful, because these oxyanions are able to move charge around using resonance. So instead of something that is barely acidic at all, like ethanol, when we have something like acetic acid, it's got a pKa of less than 5. It is quite acidic. It tastes sour when you eat it. So that's why vinegar has that characteristic acidic flavor. However, let's go to something a little bit more complex like phenol. So phenol is used in a lot of different compounds, including used as an analgesic to essentially help a strained throat. So one of the things with phenol is that it looks like it's just an amped up version of ethanol, except for now I have more carbon here. However, when it loses a proton, it ends up with a pKa of about 10. So it's a lot more acidic than ethanol. And it's hard to see it by just looking at this reaction. However, just like what we saw with acetic acid, it's all about the resonance, because it turns out if I've got a negative charge here, I can go ahead and push that negative charge over to make a double bond with the carbon. However, those electrons in the double bond have to go somewhere. So you end up with a negative charge on that ring. And on that benzene ring, we can keep pushing that negative charge pretty much over every other atom. So, well, none of these carbon atoms wants an electron nearly as much as the oxygen in that carboxylic acid group. When you have something like an aromatic ring, it helps everybody bear the load a little bit more. While nobody wants the negative charge individually, each one can take a little bit load off, and you have something in between ethanol and acetic acid. However, in addition to figuring out the strength of acids by looking at conjugate bases, we can look at the strength of bases all on their own. So let's go ahead and take a quintessential base. This is going to be amine. It is the classic non-hydroxide weak base. It's got a pKb of about 4.75. It's more than happy to steal a proton from water. However, now what we're going to see is some very kind of inverse trends. So if I put an electronegative group onto this amine, well, now that electronegative group is trying to pull electrons away from that nitrogen. So that means that lone pair can't reach out and grab a proton nearly as well. So the pKb goes up. It's not going to be as good of a base. However, if we put something like a methyl group, methyl groups tend to do the opposite. They are very poorly electronegative. In fact, they're often referred to as electropositive. They have lots of extra electrons, so they're going to make it easier for that nitrogen to use its lone pairs and reach out and grab a proton. When it does, we watch the pKb go down. It is more basic than ammonia. Well, adding a bromine makes you less basic. Now we can go ahead and take these ideas, amp them up a little bit, and add in a toluene, or add in that benzene ring. So that benzene ring, in fact, takes the bromine idea and amps it up even more, because it turns out that this aromatic ring is really good at taking up that negative charge on the ammonia, just as we saw. Adding an aromatic ring makes a molecule more acidic, which means it makes that base less basic. So it turns out by adding in that aromatic ring, we make a really terrible base. So when you're trying to figure out what makes a good acid, those things are going to make terrible bases. However, we can also look at the differences in atoms. So nitrogen, with its nice lone pair and not being too electronegative, is a pretty good base. It's more than happy to go and grab an extra proton. However, if I go to methanol, which would be a close analog, oxygen really doesn't like having an extra proton. It doesn't like having a positive charge nearly as much as the less electronegative ammonia. So this will really end up increasing the pKb, making it a very bad base. And if you make it even worse by throwing on that aromatic group, turns out phenol, while a decent acid, is a terrible base. It is going to be very unlikely to try and get that extra positive charge and grab a proton. So when trying to figure out whether something is an acid or a base, the go-to way is to actually look up its pKa's and pKb's. However, if you can't, use some of these periodic trends, figure out what makes a molecule stable or unstable. So next time, we're going to go ahead and use these pKa's and pKb's and try and figure out exactly how much protons can an acid lose. Until then, take care.